Hello everyone, I am Preeti and today I am here for give my presentation on the topic scanning electron microscope. So let's start. So the first question is why we use SEM? What SEM does? SEM gives the topographic, morphology, composition and crystallographic information of the specimen. Let's discuss these four terms one by one. The first one is topography. Topography is the surface feature of an object or how does it look like, what is its texture. And the morphology is the shape, size, and arrangement of the particles in the specimen. The third one is composition. Composition is the elements and the compounds that present in the sample. That means the sample is composed of what elements and the compounds. The fourth one is the crystallography. That means how the atoms are arranged in the objects, their direct relation between these arrangements and the material properties. So, what SEM does? SEM is a type of electron microscope that produces image of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, produce signal that contains information about topography and composition of the sample. So here is the basic components of an electron microscope on the left side. The first one is the electron source from where electron beams comes out. The second one is the condenser lens, then sample, objective lens, diffraction plane, intermediate image, projector lens, and the last one is the fluorescent screen or a photographic film. This is the basic sequence of any electron microscope. On the right side, this is the simplified ray diagram for an electron microscope showing the diffraction and imaging possibility. So the electron beams comes out from the source of electron and it falls on the object plane from where it get passes through the objective lens and then from the back focal plane where a diffraction pattern forms and these rays fall on the image plane where we get a magnified image of the sample. Now, the basic principle of the scanning electron microscope. The basic principle is that a beam of electrons is generated by a suitable source, basically of a tungsten filament or a field emission gun. The electron beam is accelerated through a high voltage and passed through a system of apertures and lenses to produce a thin beam of electrons. Then the beam scans the surface of the specimen. Electrons are emitted from the specimen by the action of scanning beam and collected by a suitable placed detector. Here is the diagram of the scanning electron microscope, and these are the basic components of this scanning electron microscope. The first one is the electron gun, then condenser lens, scanning coils, detectors, and the samples. Here we use thick sample, and the reason behind this we will discuss later in the next slides. So we discuss these points one by one. The first one is the electron guns. Electron guns are of the two types. The first one is the thermionic guns and the second one is field emission guns. Thermionic guns provide thermal energy to overcome the surface energy barrier of electron. They usually made up of tungsten, which has high melting point. And the second one is the field emission guns. The electron emission due to an electric field from a sharp point. Now the condenser lenses. SEM use condenser lens to produce clear and detailed image of the sample. Condenser lenses are made up of magnets capable of bending the path of the electron. By doing so, the condenser lens focus and control the electron beam. And after that, the scanning coils which scan the surface of the specimen. Then the detectors detect the rays come out from the specimen and identify them. After that, the sample comes at the bottom of at the bottom of this instrument. Now we understand the elastic interaction of an electron and an atom. An electron penetrating into the electron cloud of an atom is attracted by the positive potential of the nucleus and its path is deflected towards the core. As the electron comes closer to the nucleus, the higher will be the scattering angle. As the Coulomb force increases with increasing atomic number of the element, therefore, as the atomic number increases, that means more scattering takes place. Now, a question arises why we use thick samples. When the sample is thick, the electron probe doesn't penetrate through the sample. That means the electron beam scattered from the sample surface. In contrast, why we use the thin samples, the electron beam can penetrate means it can transmit from the sample. Here, some electrons are scattered back, some interact with the sample and produce other signals that are secondary electrons, backscattered electrons, Auger electrons, and the X-rays. Here is the diagram showing that secondary electrons comes from the comes closer from the surface and the backscattered electrons are within deeper from the surface. So, what are the secondary electrons? Secondary electrons are used for topographical image of the sample. They are generated closer to the surface of the sample. They are low energy electrons nearly equals to 10 to 15 electron volt. They generated from the collision between incoming electrons and loosely bonded electrons. The weakly negatively secondary electrons will be deflected by a positive pull exerted by the Faraday cage surrounding the secondary electron detector and therefore will contribute to the image formation. So, second is backscattered electrons. Backscattered electrons used for providing information of the surface composition. Backscattered electrons are also produced deep within the sample. They have a much high energy and because of this, they are able to escape from deeper within the interaction volume. Backscattered electrons will not be deflected by the Faraday cage and therefore not contribute to the image formation. This is the solid state backscattered electron detector. Here, this detector is a four-quadrant solid-state detector that is placed directly above the specimen. Now we see the concept of interaction volume. So what is interaction volume? When the electron beam penetrates into the sample, it travels some distance and up to which distance it can travel, this is the interaction volume. And this interaction volume depend upon three factors. The first one is atomic number, second is accelerating voltage, third one is the angle of incidence. Now we discuss these 3 points one by one. The first one is atomic number. When the atomic number of the material increases, that means the material with high atomic number can absorb or stop more electrons, so they have a smaller interaction volume. Now the accelerating voltage, when we use a high accelerating voltage, the electron beam can penetrate further into the sample and generate larger interaction volume. That means accelerating voltage is directly proportional to the interaction volume. The last one is the angle of incidence for the electron beam. As the angle of incidence increases, this interaction volume decreases. Here, I show the energies of secondary electron back and the backscattered electron. The energy of secondary electron is less than 50 electron volt and the energy of backscattered electron is greater than 80% of the primary electron beam. Now, this is the effect of the accelerating voltage. In the previous slide, we see that accelerating voltage is directly proportional to the interaction volume. That means if we use uh, here first one, the Z represent atomic number and E is the energy of the primary beam. If the atomic number is higher, that means the electron is absorbed or stopped easily by the material surface. So if we have high Z value, that means small interaction volume, and if we have low Z value, means low atomic number, that means more interaction volume. Now we compare both these here. In both these, atomic number is higher, but in first one we have low energy of the primary beam, and in the second one we have high energy of the primary beam. So due to the high energy of the primary beam, interaction volume is higher. As similar in both, in this case, this one has low energy of the primary beam and this one has high energy of the primary beam, therefore it have high interaction volume. Okay, now the electron beam and the sample interaction. Here we can see that carbon, iron and silver, when we compare these three elements, silver have higher atomic number as compared to iron, which have high atomic number as compared to the carbon. So, so silver have small interaction volume because it can stop the electron beam easily, and electron beam cannot penetrate further into the sample, so this has small interaction volume. Iron have larger interaction volume as compared to silver, and carbon have the largest interaction volume as compared to both these. So now the interaction volume versus accelerating voltage. Here is here we use 25 kilovolt voltage of 25 kilovolt, 15 kilovolt and 5 kilovolt. If the accelerating voltage is higher, the interaction volume is also higher. As we can see in the previous slides. So this is the total electron yield graph between the intensity and the electron energy. As we can see that secondary electrons have less energy as compared to the backscattered electrons. In secondary electrons, there is inelastic collision. Inelastic collision means there is some loss of energy when collision takes place. And in backscattered electrons, there is elastic collision. That means there is no loss of energy when collisions occur. So backscattered electrons have high energy and secondary electrons have low energy, and other electrons are also have high energy but they have very low intensity. Now a very important concept, that is contrast mechanism in SEM. Contrast mechanism are two types. This is topographical contrast and second one is the compositional contrast. Topographical contrast, both backscattered electrons and secondary electrons show the topography of the rough surface. And in compositional contrast, the amount of backscattered electrons depend on the composition of the material. The phase with composition that consists of atoms with high atomic number appear brighter. This is the topographical contrast mechanism. Both secondary electron and backscattered electron are used to show the topography of the rough surfaces. Here a concept, that is trajectory effect. That means how specimen surface is oriented with respect to the detector. The angle at which the beam strikes the specimen is important factor in determining the amount of the secondary electron escape from the specimen. Tilting the specimen may contribute to the contrast, that the electron electrons emitted from the surface facing towards the detector will be collected richly by the detector. Therefore, that side appear brighter in the image. Due to this reason, as you can see in this diagram, this left side appear brighter and this front side appear darker because the more secondary electrons are goes towards the detector easily. Therefore, this side appear brighter in the same image. This is the topographical contrast mechanism. So a very important question arises that why do edges appear brighter in the same image? From the edge of inclined surfaces, more number of secondary electrons escape as compared to the flat surface of the sample. Therefore, these edges appear brighter. As you can see in this figure, that from these edges, more number of secondary electrons escape as compared to these flat surface. Here are some examples of the same images that some edges appear brighter, one face is appear brighter due to the trajectory effects, and as is in this also edges appear brighter. Now, the effect of accelerating voltage. As the accelerating, if we use high accelerating voltage, that means due to the high accelerating voltage, we get unclear surface structure. That means more damage in the same image. And if we use low accelerating voltage, that means clear surface structure and we get the less damage in the same image. As we can clearly see in these two pictures, if we use high accelerating voltage, we get more charge up, and if we use low accelerating voltage, we get less charge up in the same image. And the last one is the advantages and the limitation of the scanning electron microscope. So discuss the advantages of the scanning electron microscope. The first one is the long depth of focus and due to the 3D effect. Second one is the large specimen size. Third is simple and rapid specimen preparation. Large range of magnifications. In the same image, we have large range of magnification. This is a very important advantage of the SEM. And now we discuss the limitations. First one is the lower resolution than the 10. In SEM, we get lower resolution as compared to 10. Usually for non-conducting specimens, metal coating is needed. Only the surface of the specimen can be viewed. We cannot view the internal structure of the sample. We can only read the surface of the specimen, and in the SEM, when we use SEM, we need high vacuum, which is difficult to maintain. Thank you so much.